Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to evaluate definite integrals involving hyperbolic functions. But before we start, why don't we look at the definitions of the hyperbolic functions first, and we have a table for that. Please refer back to this. And here, sine and cosine are written in terms of exponential functions. So since all other four hyperbolic functions are also written in terms of sine hyperbolic x and cosine hyperbolic x, they are all written in terms of exponential functions. And as well, I want you to recall the hyperbolic identity. So we have a table for that, and we may utilize some of those identities along the way. I don't want to give you any hints at this moment, but these are all the ingredients that we're going to use in this video. All right, let's get started.
All right, so let's take care of the very first definite integral. That's the integral from 0 to 1, cosine hyperbolic squared x dx. Well, first of all, cosine hyperbolic squared x dx is a non-negative function. So you may treat this integral as the area between the curve cosine hyperbolic squared x dx for the part of the graph stuck in between 0 and 1. So it's the area between the curve and the x-axis. And here is just what I'm just telling you, right? So blue curve is cosine hyperbolic squared x, and x-axis is y equals 0, essentially. Okay, so we're talking about this area here. So the question is like, what is the value of this area? And that value is determined by this integral here. Okay, so if we evaluate this integral and get a number at the end, because this is a definite integral, and that number is the value of the integral. Okay, so now the question is like, what are we supposed to do to be able to integrate cosine hyperbolic squared x dx? Okay, for that purpose, please go back to or refer back to one of the formulas here that I call them like power reducing formulas for hyperbolic functions in the table of hyperbolic identities here, and that's the one at the very left corner over there. That cosine hyperbolic squared x is written as 1 plus cosine hyperbolic 2x divided by 2. That is exactly what I'm going to use here. So instead of this integral here, I'm going to write that as 1 plus cosine hyperbolic 2x over 2 dx. And as I always do, first I'm going to attack the indefinite integral version of this. And once I have the result for it, I'm going to use it towards evaluating this definite integral by using the fundamental theorem of calculus. Right, here we go. Let me just put the dx back here. Okay, so this is two integrals. In fact, one is an easier one, 1/2 dx, and the other one is maybe 1/2 out here, 1/2 cosine hyperbolic 2x dx. Okay, let me just put that in parentheses. All right, let's have like a little u substitution here. So let's call this guy to be u, so that u equals 2x, du equals 2 dx, so that this integral here is 1/2 plus, well, 1/2, another 1/2 coming from dx, right? So that makes it like 1/4 outside. Cosine hyperbolic u du. And let's see what the integral of cosine hyperbolic u is. There we go. That's the very first integral here. Okay, that's sine hyperbolic u plus c. Okay, let's go back to here and then write this as well. First of all, this is x over 2. This is 1/4 sine hyperbolic u plus c, and then putting the u back here, you have x over 2, 1/4 sine hyperbolic 2x plus c. And towards the use of fundamental theorem of calculus for the evaluation of this definite integral, I don't need to carry forward the c. Okay, so I can go ahead and then write this as x over 2 plus this, with the lower limit being 0, upper limit being 1. Okay? Let's plug in the upper limit. That's 1/2 plus 1/4 sine hyperbolic 2. That's the upper limit. Minus, well, if you plug in 0 for x, that's 0 over 2, 0. 1/4 sine hyperbolic 0. Okay? And go ahead and use your calculator if you want to, but make sure that this is already 0, because sine hyperbolic 0 is already 0. So this is almost like sine 1/2 plus 1/4 sine hyperbolic. You can just leave it as is. I am completely fine with that, or you can go ahead and use your calculator and get an approximate value, but since I'm fine with it, I'm going to leave it as this. This takes care of part A, and remember to use hyperbolic identities and practice with them. As you see that one more time, we used an hyperbolic identity in this exercise, in the list of exercises here. So and this time we used the power reducing formula for hyperbolic functions. All right. This is the end of part A. To see what I'm going to do for part B, please move on to my next video. Bye.